Hello viewers, in this part of the program I am going to discuss soil moisture constants. When water is added in the soil, it is subject to various forces. Water is not static in the soil, and because of its nature, it moves from one direction to another direction. Certain moisture contents in the soil are having particular significance in agriculture, and these moisture contents are known as soil moisture constants. Water content of soil under field conditions is not static. It is subjected to pressure gradients and vapor pressure differences that cause it to move. It has been found experimentally that certain moisture contents are of particular significance in agriculture, and these are often called soil moisture constants. The concept of soil moisture constants facilitates decisions in irrigation water management, and that is why soil moisture constants are examined so that the decisions on irrigation scheduling may be taken. The soil moisture constants are gravitational water, field capacity, permanent wilting point, hygroscopic water, and moisture equivalent. As far as gravitational water is concerned, it may be described that the water under the force of that moves under the force of gravity. When water is added to a dry soil, it is distributed around soil particles where it is held by adhesive and cohesive forces. It displaces air in pore space and eventually fills the pores. When all the pores, micro as well as macro, are filled with water, the soil is said to be saturated and is at its maximum water holding capacity. Water in the macropores that moves downward freely under the influence of gravity beyond the root zone is called gravitational water or free water. This water is not available to the plants. When the soil is saturated due to continuous rainfall or heavy irrigation, the free water moves from root zone to deep soil profile, and ultimately that is not available to the plants. Field capacity. When the supply of water in a saturated soil is stopped, water continues to drain from the larger pores for a day or two and become negligible thereafter. The macropores are then filled with air. The micropores are still filled with water. Water is retained because of capillary force. This water is called capillary water. The soil is then said to be at its field capacity. Field capacity is the upper limit of available water, and it is very important for irrigation scheduling in different crops. Whenever there is deficit of water, then the water is added to the soil for the crop growth up to the level of field capacity of that particular soil. The soil water potential at field capacity ranges from minus 0.1 to minus 0.3 bars or minus 0.01 to minus 0.03 megapascals. Field capacity is considered as the upper limit of water availability to plants. Soil water at field capacity can move in any direction, but always in the direction of increasing tension. The term field capacity, field carrying capacity, normal moisture capacity, and capillary capacity are often used synonymously. In case of field capacity, generally the water is retained by micropores and the force with which water is retained in micropores is almost equivalent to that of the gravitational force. And because of this equivalence in forces, the water is retained in the micropores, and this water retained in micropores is generally used by the growing plants. Field capacity can be determined in laboratory as well as under field conditions. The method for determination of field capacity is described. Field capacity is determined by ponding water on the soil surface in an area of about 2 to 5 square meter and permitting it to drain for 1 to 3 days with surface evaporation prevented. Evaporation may be prevented by spreading a polythene sheet or a thick straw mulch on the ground surface. 1 to 3 days after the soil is thoroughly wetted, soil samples are collected with an auger from different soil depths at uniform intervals throughout the wetted zone. The moisture content is determined by gravimetric method. In this way, in case of sandy soils, only 1 day is sufficient for determination of field capacity, whereas in clay soils, the soil comes to the field capacity after 3 days. And one important thing is taken into consideration, that the surface of the soil is covered by polythene sheet or straw mulch, so that the evaporation process is prevented, and only there is downward movement of water, and whenever this downward movement of water is almost ceased, then the soil comes at field capacity, and at this point the water content at different depths is determined, and that water is the field capacity of that particular soil. The next soil moisture constant is permanent wilting point. Field capacity is the upper limit of available water, whereas permanent wilting point is the lower limit of available water. As the soil water tension increases, the water availability from soil to the plant gradually decreases. At 15 bar of soil water tension, plants absorb very small quantity of water. During daytime, plants show wilting symptom because of heavy loss of water by evaporation and transpiration. However, plants, if supplied with water, regains its growth. Moisture content of the soil at this stage is called permanent wilting point or wilting coefficient. At 60 bars, plants cannot absorb any moisture and they die. Soil moisture content at which plant die is termed as ultimate wilting point. At permanent wilting point, small amounts of water can be removed from the soil by plants, whereas at ultimate wilting point, soil moisture is not available to plants. The permanent wilting point and the field capacity, these are important soil moisture constants, and the amount of water as well as the time of water application is decided by these two parameters. In case of field capacity, soil is irrigated in such a way that the soil regains its moisture content at field capacity, and when the water decreases from field capacity to permanent wilting point, the gradual decrease in availability of water to the plant is also there. Determination of permanent wilting point. Permanent wilting percentage is determined by growing indicator plants in containers, usually in small cans holding about 600 grams of soil. Sunflower plant is commonly used as the indicator plant. The plants are allowed to wilt and are then placed in a chamber with an approximately saturated atmosphere to test them for permanent wilting. Here, for determination of permanent wilting point, sunflower is taken as an indicator plant, because the sunflower is having wide leaves and the wilting symptoms can be identified accurately in sunflower plant. Therefore, sunflower is used as an indicator plant for determination of wilting point. The residual soil moisture content in the container is then calculated, which is the permanent wilting percentage. The determination of moisture content at 15 atmosphere tension, which is the usually assumed value of permanent wilting point, can be done by the pressure membrane apparatus. So, these are the two methods of determination of permanent wilting point: by growing sunflower plant or in the laboratory by using pressure plate membrane apparatus. Hygroscopic water: evaporation from surface and moisture absorption by growing plants reduce the amount of water in the soil until water no longer moves because of capillary force. It is held so tightly as thin film around soil particles that cannot be used by plants. This water is called hygroscopic water. Hygroscopic water can be defined as the water that gets absorbed from an atmosphere of saturated water vapors owing to the attractive forces of the surface of particle. Hygroscopic water remains at a tension of 31 bars. So, the ultimate wilting point comes at 60 bars, whereas hygroscopic water content remains at 31 bars. At hygroscopic water content, the water adhesion forces with soil particles are quite high, and at this point the availability of water to the plants is drastically reduced and the plant growth is adversely affected, and at ultimate wilting point ultimately the plant growth ceases due to unavailability of water. Moisture equivalent: moisture equivalent is defined as the amount of water retained by a sample of initially saturated soil material after being subjected to a centrifugal force of 1000 times that of gravity for a definite period of time, usually half an hour. To determine the moisture equivalent, a small sample of soil is whirled in a centrifuge with a centrifugal force of 1000 times that of gravity. The moisture remaining in the sample is determined, and this moisture is known as moisture equivalent. This moisture content, when expressed as moisture percentage on on-dry basis, gives the value of the moisture equivalent. In medium textured soils, the values of field capacity and moisture equivalent are nearly equal. In sandy soils, the field capacity exceeds the moisture equivalent. In very clay soils, the field capacity is generally lower than the moisture equivalent. So, in this way, moisture equivalent is almost equal to field capacity in medium textured soils, whereas in case of sandy soils it is less, and in clay soils it is higher than that of field capacity. This is the diagram showing the water content at different soil moisture constants in sandy loam soil and silt loam soil. Here you may see that in case of silt loam soil, the available water is more in comparison to sandy loam soil, and at on dry condition the water is almost equal. But when the water content is increases, the water holding capacity of silt loam becomes higher in comparison to sandy loam soil. This diagram also shows the relation of soil texture with different soil moisture constants, and the water retaining capacity of all soils increases with increase in clay content in these soils. In case of sand, the available as well as unavailable water is less in comparison to clay loam and loam soil. Available water is very important for plant growth point of view. Soil moisture between field capacity and permanent wilting point is referred to as readily available moisture. It is the moisture available to plant use. In general, fine textured soils have a wide range of water between field capacity and permanent wilting point than coarse textured soils. And because of the variation in water availability in different texturally soils, the irrigation interval vary. In case of sandy soils, frequent irrigations are required, whereas in case of heavy textured soils, irrigation interval is more. In contrast, sandy soils with their larger proportion of non-capillary pore space release most of their water within a narrow range of potential because of the predominance of large pores. For irrigation system design, the total available water is calculated for a soil depth based on the root system of a mature plant of the crop to be grown. In sandy soils, because of the more number of the macropores, most of the water is drained due to the force of the gravity and little water is retained, whereas in clay soils, due to large number of micropores, most of the water is retained in micropores and that is available to the growing plants. For the convenience of understanding, I am quoting one example. The soil is having field capacity 23.2%, moisture content at the time of irrigation is 12%, depth of the soil is 30 centimeter and the bulk density of the soil is 1.5 gram per cubic centimeter. Then to calculate the water content for raising this particular moisture up to the level of field capacity, what quantity of water will be required? So, in this case, deficiency of moisture will be 23.2 minus 12, that is 11.2%. This 11.2% water has to be added in the soil so that the soil will come to the field capacity. So, here the depth of water to be added will be 11.2 multiplied by 1.5, that is bulk density, multiplied by depth of the soil, that is 30, and divided by 100. The depth of the water required to bring the soil up to field capacity will be 5.04 centimeter. Theories of water availability. Optimum growth of plants takes place in most soils when soil moisture content is kept near field capacity. Some workers hold that water is equally available over the entire range of available soil moisture, while others consider that plant growth is affected with decreasing water potential from field capacity to permanent wilting point. Bulk of evidence supports the latter view. The third approach is that there is a critical moisture level in the available moisture range, and beyond this there is decreasing availability of moisture as permanent wilting point is reached. A significant decrease in growth of plants is noticed below this critical moisture level, known as critical moisture tension. Yield of several crops are not reduced if irrigation is scheduled at 50% depletion of available soil moisture. This concept of availability of water to the plants has been shown by this figure. In this, all the three approaches have been shown. The A approach is that critical moisture tension. Up to critical moisture tension, availability of the water to the plants is sufficient, but at critical moisture tension and later on, the availability of water to the plant decreases constantly.
Yes, sir.
All these three approaches have been described by this diagram. According to the first approach, that has been shown by A. According to that approach, water availability is constant from field capacity to permanent wilting point, that is equal availability of water. According to next theory, water availability is full up to certain level, and that level is known as critical moisture tension. That has been shown partly by A and partly by C. And after critical moisture tension, the availability of water constantly decreases. According to third approach, there is constant decrease in water availability from field capacity to permanent wilting point. And according to the view of most of the scientists, this critical moisture tension approach, that is A plus C, is more scientific in comparison to other approaches. In this part of the program, I have discussed soil moisture constants, soil water content at gravitational water, field capacity, permanent wilting point, hygroscopic water, moisture equivalents is having particular significance, and soil water content at these points is known as soil moisture constants. The difference in water content at field capacity and permanent wilting point is known as available water. This water having particular significance for the plant growth. And for irrigation scheduling, soil moisture constants are of particular importance. Hope you have enjoyed this lecture.